Picking up from where we left off on Friday, an isotope is an element that has the same atomic number, but different atomic masses. So they have the same number of protons, and therefore they're the same chemical element, but they have different atomic masses. This is because they have different number of neutrons. So for example, carbon-12 and carbon-14 are both carbon. They're both element number 6. They have 6 protons, but the nucleus of carbon-12 contains 6 neutrons because 6 and the 6 protons make 12, whereas the nucleus of carbon-14 contains 8 neutrons, where 8 neutrons and 6 protons make 14. A radioisotope is an isotope that undergoes radioactive decay. So not all isotopes or even elements are radioactive, and particular ones that are able to undergo alpha, beta, and gamma decay, which we're going to talk about next, would be considered a radioisotope. The assignment for this section, talking about number of protons, neutrons, electrons, and nuclear notation, would be on page 503. And I would want you to do number 26, 27, and 28. I'm going to continue on into different types of decay, though. So a force called the strong nuclear force is the force that holds the protons and neutrons together in a nucleus. This force is much stronger, than electrical forces. So we talk about positives attracting negatives. Those would be electrical forces. The strong nuclear force is stronger than a positive attracting a negative. So looking at the balanced forces in beryllium, beryllium has electrical forces, and those would be the force of repulsion between protons. Remember, of course, protons are both positive, so we would have a positive repelling a positive. Now, protons all exist within the nucleus, and they are tightly packed. So how is that possible if they repel one another? So in come the strong nuclear force. There is an attractive force acting between neighboring protons and neutrons, so a positive and a neutral. So neutrons play an important role in the composition of a nucleus. So they dilute the electrostatic repulsion of positive protons. So they reduce the positive, okay, because they are kind of getting in between there. They also increase the strong nuclear force by acting like glue to hold the nucleus together. So we're going to talk about 3 different types of decay. So we take a parent isotope, so a parent element, and they undergo or can undergo radioactive decay. They can undergo alpha decay, they can undergo beta decay, and they can undergo gamma decay. And we're going to talk about each one of these. But the particle they're giving off is represented here. So what you need to know is that if a nucleus becomes unstable, it will undergo a radioactive decay in the form of either alpha, beta, or gamma decay. These symbols are from the Greek alphabet. So alpha looks like a little fish, beta is a bee with a long tail, and gamma is a Y that's been crossed over. So we'll start with alpha decay. In alpha decay, an alpha particle, which is a particle with 2 protons and 2 neutrons, is given off. Something with 2 protons and 2 neutrons is really a helium nucleus. they've kind of written it backwards here in our notes, noting that we would actually write with the numbers out front. And it's given the symbol alpha 2 plus because protons have a charge of 2 positive, or sorry, each one is 1 positive, so 2 of them would be 2 positive. The release of alpha particles during nuclear decay is called alpha radiation. Beryllium-8 is an unstoppable nucleus in comparison to beryllium-9. So this difference of 1 neutron reduces the strong nuclear force keeping that atom together and causes the nucleus to decay into 2 alpha particles. So we start with our unstable nucleus of beryllium-8, noting that beryllium has 4 protons to begin with. When it undergoes alpha decay, remember, will produce a helium. And so what we notice is that it actually produces 2 heliums. What I want you to notice is that if I add the numbers up at the top in a reaction, in a radiation reaction, I'm seeing that 4 plus 4 is equal to 8. So this is the mass number, okay, or the mass. 2 and 2 on the bottom add up to 4, the total number of protons. So we'll notice that the top numbers add up to the first top number, and the bottom numbers will always add up to the same bottom number. One other thing to note is that there is a list on page 8 of your data booklet that contains what all of the particles are. So it tells you that if something undergoes alpha radiation, it is emitting this particle from its nucleus. So again, what this means is that we have kicked out 2 protons and 2 neutrons so that it adds up to 4 total from this nucleus. And then we write whatever's remaining. It just so happens that in beryllium, we made 2 heliums. So let's take a look at one other example here. So we will write the balanced nuclear equation for alpha decay of radium. So a helium nucleus is given off of the parent as the parent or original element is transmuted. Now, transmuted simply means that we have changed one element into another. So something the alchemists were always trying to do way back in the Middle Ages, they were trying to create gold from other elements. So we're going to take a look at this example here. We're given the parent element, and it says that it's number 88 with symbol Ra. If you look in your data booklet on your periodic table, number 86 is radium. It has that symbol Ra. We call this the parent element, what we are starting with. It undergoes alpha decay and produces a helium nucleus. Again, we know that this would be the particle produced in alpha decay because we looked at our data booklet. So I know that this is produced, and we need to figure out what is left. So to determine the daughter element's mass number, we will subtract 4 from the parent element's mass number. So the parent element's mass number is 226. Remember that we have to be able to say that the 226 on this side is equal to whatever the top numbers are on this side added together. So if we have 226 on this side, we already have 4 on the product side, therefore we need to account for the rest. So we will subtract 4 from the parent's mass number. This is the amount of mass lost to making that helium nucleus. So we started with 226, we'll take away 4, and we're going to get 222. To determine the daughter element's atomic number, we're going to do the same thing, but looking at the bottom numbers. So we're going to subtract 2 from the parent element's atomic number. Our parent element's atomic number was 88. We're subtracting 2 because of the 2 in helium, and we get 86. 86 will tell me what element we have made. 86 is the atomic number for radon. So once I've discovered that, I can write this information. So we had 222 from subtracting 4 from 226. And our 86 from subtracting 2 from 88. And then we simply looked up our element, and that was radon. So writing the full balanced equation for that is on the top of our next page here. Our balanced equation would be our parent element, radium, becoming radon and our alpha particle. Okay, so one more time, just to label, this was our parent. The daughter is what we have created. And helium was our alpha particle. The mass numbers in both the reactants and products have to equal the same when we add them up. And our atomic numbers in both the reactants and products will add to be the same. Okay, we're seeing that mass is conserved. So let's try an example of that on our own. Many smoke detectors contain the isotope americium-241. Alpha particles emitted during the decay of americium-241 ionized molecules in the air, allowing an electric current to flow between the two plates of the smoke detector. During a fire, smoke particles that come between these two plates interfere with the current, setting off the detector's alarm. So state the process that produces an alpha particle and write the balanced nuclear equation describing the decay of americium-241 that results in an alpha particle and another product. So the process that produces an alpha particle, you could either write alpha decay or alpha radiation. Either or would be acceptable here. And then we're going to write the balanced nuclear equation. So let's set this up with our reactants and our products. So americium-241, again, looking in your data booklet, 241 being the approximate atomic mass. I find americium, Am, is element 95. So what we're going to write would be its symbol, Am. And we're using americium-241, not the 243 that's listed in our data booklet, simply because they told us which isotope of americium we're using. And then I'm going to write its atomic number below, which was 95. So our products, we are making an alpha particle, which is helium. So we have 4, 2, and the symbol for helium. And then we're going to write the general formula for the unknown or the daughter element. So that was the AZX notation. Okay. So from here, let's start with the mass number. So the numbers on top. So we'll start with our 241. So we'll take 241 and subtract the 4 from helium. And we get 237. So that is the mass number for our daughter element. So that represents A. Next, we're going to do that, but for the atomic number of the daughter element. So we're going to take our 95 and subtract 2 protons from helium. And we're going to get 93 protons. So that represents Z. Once we have that piece of information, I can determine what element we have created. So the element with 93 protons is neptunium. So NP. NP is neptunium. It has 93 protons. So to finish up our equation here, we're going to write the balanced equation, really just copying what we have here, but filling in our information for X. So our final answer will be 241.95 americium makes helium and 237, oops, I don't need the over symbol, 93 NP, neptunium. And that's our final answer for this. Some practice for this is found on page 506. Oh, I'm running out of room here. So page 506, and that's 29, number 29 and 30. I would suggest that you take 10, 20 minutes now to take a look at those examples, because once you get comfortable with alpha decay and how we have calculated or discovered who the daughter element is, beta decay and gamma decay come fairly naturally. All right, now that you've had a moment with alpha decay, let's move into beta decay. Beta decay involves an electron, also known as a beta particle, that is given off as the parent or our original element is once again transmuted. Remember that this means that one element is changed into another element. So this electron or beta particle is produced when a neutron breaks up into a proton and an electron. So one thing to note here is that when we're talking about an electron, this particle is still coming from the nucleus. So this isn't an electron like in the cloud orbiting our element, so where we would normally find electrons. This is a particle generated within the nucleus of our element. So beta radiation involves a stream of beta particles that are emitted from an unstable nuclei. I'll use a different color here just to be clear. So an unstable nuclei undergoes beta decay. So the beta particle is really, again, an electron, and it is given by the symbol for an electron, where it is the opposite of a proton, okay, and it has no mass. We can also write B. We'll use electrons in our notation, but again, a beta particle can be denoted by a B. So what we see, again, is a neutron from our nucleus that breaks into a proton and a beta particle or an electron. So we have conserved charge. Our positives and negatives are still equal. We've just lost an electron from our element. So for alpha decay, we talked about beryllium-8. For beta decay, we're going to talk about beryllium-10. So beryllium-10 is also an unstable nucleus, but it undergoes a different type of decay. It will decay by emitting a negative particle called a beta particle, and is really an electron that comes from the nucleus. So we see that beryllium-10, again, still has 4 protons and a mass number of 10 because that is what's given. It's an unstable nucleus that creates a beta particle, and we need to determine what its daughter element is. So remember that the mass numbers in the products must equal the mass number in the reactant. So because a beta particle has a mass number of 0, we know the mass number of our daughter element will still be the same, so 10. Now, our atomic number in the reactants has to equal the sum of the atomic number in the products. So -1 and 5 add to 4. And because we have 5 protons, an element with 5 protons in our data booklet periodic table is boron, and therefore we know that we have created boron 10. We always write the mass number next to the isotope name. So in beta decay, the number of nucleons, remember, that's protons and neutrons total in the nucleus, doesn't change, but the atomic number does. This is because a neutron becomes a proton. So there's just a switch of one particle within the nucleus. A neutron becomes a proton, and our beta particle is emitted. So we'll look at an example where we have phosphorus 34. Phosphorus has an atomic number of 15, and we're looking at the mass number of 34. This is our parent element. It undergoes beta decay and emits this electron or beta particle, which again, we can find the formula or symbol for this in our data booklet. And it will also create a daughter element, and it's our job to figure out who is the daughter element. So the daughter element has the same mass number as the parent element because no mass is lost in a beta decay. So in this case, the daughter element's mass is 34. The daughter, there we go. The daughter element's mass number is 34. To determine the daughter element's atomic number, we will add 1 to the parent element's atomic number. This is the number of protons formed during the beta decay process. So this was because, for instance, we had 15 protons in our reactants, and we had -1 from our products plus some sort of number. I think that's Z in our representation. To solve for Z, I had to add 1 to both sides. This is how we added 1 to 15 to get 16. So in this case, Z is equal to 16. The element formed in the beta decay process is therefore, in this case, atomic number 16 comes from sulfur. And the complete nuclear equation is represented here. So we start with our parent element. We have listed our daughter element with the same mass number and our new number of protons and our beta particle. Once again, 16 plus -1 is 15. 34 plus 0 is 34. So mass is conserved. We've written the correct equation. Carbon-14 is a radioactive isotope that emits beta radiation. Carbon-14 is found in the atmosphere and eventually finds its way into living systems. Once a plant or animal dies, the amount of carbon-14 remaining in the tissue can be used to estimate the number of years that have passed since the organism's time of death. This is done by using the half-life of carbon-14. To get a clearer picture of human history, archaeologists use carbon-14 dating to estimate the age of ancient remains, like teeth or bone fragments. So they use this nuclear equation to determine how much carbon-14 is left and look at periods in time that would have had a specific amount of carbon-14, just working backwards. So we use this information to write a balanced nuclear equation for the beta decay of carbon-14. I think now that you're a little bit more comfortable with nuclear equations, I would recommend pausing this video and writing the nuclear equation for this. So pause your video now and give it a try on your own. Now that you have a moment to try it, let's write the beta decay equation for carbon-14. So carbon is C, carbon-14 would be its mass number, and carbon always has 6 protons. For something to undergo beta decay, it needs to create an electron and some sort of daughter element. So to calculate A, I'm going to say that there were the mass number in the reactant side was 14, and the total mass number in the products must be the same, so 0 from the electron plus A. From that equation, we can clearly see that A is equal to 14. So therefore, A is equal to 14. In our atomic number, so the bottom numbers here again, 6, -1, and Z, we can say that 6 from our reactants is equal to -1 plus Z from our products. And solving, I add 1 to both sides to calculate, cancel the -1. And I'm left with Z is equal to 6 plus 1, which is 7. So when I get 7, I need to look at what element has the atomic number 7. So this is the atomic number for nitrogen. Therefore, when I write my final equation, I can say carbon-14 undergoes beta decay to create a beta particle, and nitrogen-14. For practice here, take a look at page 507, number 32 and 33. We will pick up where we left off here and touch on gamma decay tomorrow in class.